Hello, today I'm talking about my thesis, the parametric estimation of randomly compressed functions. So first I'll start with an introduction or a recap if you're familiar with some of this work, and then I will talk about a twist on this approach that we're talking about, which is compressive subspace matching. After that we'll go into compressive match field processing, which is the main application of this thesis, and then we'll follow that up by an extension to multi-source localization. Then we'll talk about the theoretical analysis. What can we say about this approach in theory? And finally, we'll conclude with some open questions. So what do we mean by compressive sensing? Well, this is sort of the standard setup for compressive sensing. We have some long vector x, where most of the zeros are known, most of the entries are known to be 0, and there's only a few non-zero elements. We're trying to estimate those, and we do that using this fat rectangular matrix phi. So we make this observation y, and there's in most k non-zero terms in x naught. Then under certain conditions on phi that we'll talk about in a second, we'll show that we can accurately recover our signal using this L1 minimization subject to these constraints here. This is just a constraint on the residual error between y and phi x. Usually the reason we want to do this is because we can simplify the acquisition by enabling something like 1,000 measurements for a length million signal, something like that. And that's going to allow us to build simpler hardware usually. And this naturally extends to dictionary sparse models, so we don't need X to be literally sparse as long as it's sparse in some basis. So what does that look like, for example? So this is a signal that is sparse in the Fourier domain. And so as long as we have a signal which is sparse in some known basis, it doesn't have to be the Fourier, then we can recover it using this type of approach. Okay, so the success of this type of L1 minimization is tightly related to this notion of the restricted isometry property. So what does this mean? This means that for all S-sparse signals, then if you pass them through this operator phi, that they preserve their norm, and in particular that distances between points preserve their norm. So if 2 points are close in the image of phi, if and only if they're close in the domain. So we can ensure this for matrices with IID Gaussian entries, and we only require that m is at least something like S log n with some extra terms in there. Okay, so with this notion we're going to talk about the main result of, one of the main results of compressive sensing established by Candes, which says that if you do this type of L1 minimization, subject to this 2-norm constraint, then, and as long as you have a phi matrix that satisfies this RIP property with delta 2s less than or equal to square root of 2 minus 1, then this estimate x hat, x star, satisfies this inequality. So this is a difference between the ground truth and our estimate, and it's some weighted sum that depends only on the norm of x minus xs. Xs is the S-term approximation, the best S-term approximation to the true signal S, and this noise term eta. So notice in particular that if there's no noise, and if your signal is exactly S sparse, then this result guarantees that you will perfectly recover your signal. So let's revisit this idea though, because although this is a sparse signal, this is a sum of 2 sinusoids, this is a signal that's not quite sparse. So this is the same signal, except that it's now it just so happens that these 2 frequencies no longer lie exactly on grid points, and because of this you have DFT leakage. So now our signal is no longer sparse, and this result tells us that we're going to pay a penalty in terms of this 1 norm here, which is the difference between x and its best S-term approximation. But this is somewhat unsatisfying because there shouldn't really be an approximation error here. It's just that perhaps we had a bad model. So we're using a sparse model when perhaps we should be using a parametric model. So that's the main point of the thesis that we're talking about today. We want to avoid this approximation penalty by solving a parametric problem instead. So instead of doing standard parametric estimation though, we're going to do compressive parametric estimation. So parametric estimation just simply finds the best parametric function f that matches some data function h. And instead we're going to find the closest function f to h in compressed space, meaning after it's been compressed with this operator phi. And so what does our set look like now? It's no longer sparse elements. There are now elements that are parameterized by some multi-dimensional parameter theta that lies in capital theta, which is some subset of Rd. So it's some d-dimensional parameter vector that parameterizes our function set. And for our purposes, we have a one-to-one correspondence between theta and f. So estimating theta is the same thing as estimating f and vice versa. Okay, so let's relate this back to standard compressive sensing. So up top we have shown the compressive parametric estimation, and this is equivalent to, I mean, it's if you had a function set f that only consisted of sparse elements, then that would be exactly L0 minimization. And if you had a function set that only consisted of functions with bounded one norm, then this would be classical compressive sensing. So all we're doing is generalizing this to a more general parameter set. So in general, this will not be convex. Our function set won't be convex, and that means that we can no longer certify optimality locally, and we no longer have fast solvers that will solve this approach. So sometimes we'll have grid searches that will be possible for small numbers of parameters, and those will be the applications we'll be talking about today. And so what do we mean about our random projection? So in this case, we have, in the classical case, we have matrices that are m by n. And so in the case that we're talking about today, these just become arbitrarily finer until you get white noise. And of course, this is just a generalization of the m by n matrices. And so in the finite dimensional case, you still have classical m by n random matrices. Okay, and we want to emphasize that there are interesting variations on this as well. So it doesn't have to be literally an IID matrix. It can be, for example, something, white noise that is time limited approximately using some sort of window function. So imagine if you want to window your white noise process with a Gaussian function, so you don't have to run a white noise generator forever. Here you just simply apply this Gaussian window to it, and it's the same as if you had applied the Gaussian window to the function yourself. So now it's as if you have a new function class that has been windowed by these Gaussian functions. And we can play this trick for any diagonal operator W, or more generally, any Hermitian operator. So this could be a windowing the frequency domain, for example, that will give us some finite resolution noise process.